and today I'm going to be talking about Sapling, which is a network upgrade that's slated to activate later this year, hopefully in October. Just to kind of give a little bit of a recap, Sapling is a network upgrade, but we like to codename basically all of our major releases. The first release that we did in October 2016 was nicknamed Sprout. I believe we came up with that because it kind of symbolizes like a fragile but optimistic beginning. And then nothing really happened. Well, a lot happened actually if you listen to Nathan's talk for about a year and a half. Lots of releases and fixes and tiny adjustments and stuff like that, but as of yesterday, we finally activated Overwinter, which is the first network upgrade, and it went successfully, which is amazing. So in about, I don't know, 20 weeks or whatever it is, in October of this year, we're planning to activate Sapling, which is a much more significant network upgrade. It will be, when it's activated, the product of over 2 years of cryptographic engineering and design work and auditing and so forth. And it kind of started out as a bunch of different pet projects where I and others were looking for ways to improve the performance of ZK snarks and kind of push the boundary of what's possible with ZK snarks. We're also trying to improve the parameter setup, because ZK snarks need this parameter setup, the ceremony. So I wanted to make it much more scalable to perform these setups, much more robust against attackers. And also I was kind of looking into these other kind of miscellaneous performance things and curve security and stuff like that. So it kind of all came together, and thanks to a bunch of really amazing cryptographers and our company and in academia, we were able to kind of bundle it all together into one big upgrade this year. So just to kind of recap, the way that Zcash works is users send money to each other and from each other using payment addresses. There's two different kinds of payment addresses in Zcash. There's transparent addresses that start with a T, so we sometimes call them T addresses. These are basically Bitcoin-style transactions, so everything is exposed publicly, so you see the value, the source and destination of funds. Then there's shielded addresses, and shielded addresses are basically what we built Zcash for. They use the ZK snark cryptography and all this exotic stuff and zero cash and so on in order to protect people's privacy. So if transactions involving Z addresses have this very, very strong privacy guarantees, the strongest that we can make them on chain. And so these addresses start with a Z, and so we sometimes call them Z addresses. Things get pretty complicated when there are transactions that involve both transparent addresses and shielded addresses. And it's not very clear sometimes what the privacy implications are, so it's not really ideal user experience from that angle. So the original release of Zcash, the Z addresses that came with it, they look kind of like this. Besides being long, which isn't too much of a big deal, they're pretty slow. So if you want to create a transaction that sends or receives, sends or spends money that involves this address, then you have to spend minutes of CPU time. On my desktop at home, it takes about 40 seconds to construct a proof. Depending on what you're doing, it could take multiples of that. It also requires a lot of memory, a lot more memory than what you would have just sitting around on a phone sometimes. We've improved it over time. We've made it closer to about a gigabyte, but it used to be about 3 or 4 gigabytes. So these are serious impediments because we really need privacy by default in Zcash. We need it to be efficient enough to create shielded transactions because if users don't understand the privacy implications of their transactions, then it's not good. It's not good user experience, and they might be using transparent addresses without realizing that the privacy guarantees are not strong at all. And so there's two kind of important steps to take in order to make sure that we have privacy by default, I think. The first is to actually make the shielded transactions cost competitive with the transparent addresses. In order to do this, we have to do a bunch of cryptographic updates and improve performance and so on, but it's doable, and that's kind of the focus of the Sapling upgrade. Not in the Sapling upgrade, but hopefully in a future upgrade, we also need to address feature parity. So we need to add features like shielded multisig and things that businesses need, so that eventually we can have shielded transactions that do mostly what, or perhaps some superset of what you can do with Bitcoin transactions, with transparent transactions, and we can get rid of the transparent transactions entirely. That would be nice. So the Sapling upgrade has kind of two major kind of separable components. The first one is that we're actually just making the ZK snarks faster. So Zcash is built on, or the shielded transactions are built on top of these very complicated, cool cryptography, zero knowledge proofs, and we need to make them faster, and we have a lot of different ways we can make it faster, and we kind of combine them all as much as we can, while being as conservative as possible as well. So kind of the three major things are, we're replacing the elliptic curve that we use from what we use currently in Zcash. We're replacing it with a new one, a new pairing-friendly elliptic curve that these snarks use. We're also replacing the proving system itself. So the Zk snarks have a certain construction, and we're replacing it with a newer construction that has shorter proofs and so on. And we have a new parameter setup, which I'll talk about in a second. So as far as the elliptic curve is concerned, so obviously Zk snarks need these specially designed elliptic curves, and they actually have to be tuned a little bit so that snarks work really efficiently with them. The one that we currently use is called Alt-BN128, and just a note for anyone who comes up with new elliptic curves in the future: please don't put the conjectured security level of your curve in the name, because it ended up that it was not really 128 bits under really conservative assumptions. To be honest, it's close to 128 bits in practice, but under some conservative assumptions about kind of future advances in cryptography, it could be as bad as 100 bits. We don't know. So we wanted to switch to a new curve, and this is kind of how Sapling started. Shortly after launch, I was looking into all the different kinds of categories of curves and so on that we could switch, and I wanted to make sure that we switched to one that didn't sacrifice performance but improved security just enough that we could feel comfortable with, predicating a huge network upgrade, something like Sapling, on a strong foundation. So that's where BLS 12381 came from. Roughly as efficient in practice as the implementation that we had of our old curve, more secure. It's closer to 120 bits under those same conservative assumptions, though in practice is basically 128-bit security level. And it's also tuned for ZK snark performance and has a bunch of cool little features which are too technical for this talk. But so the next thing, obviously, we have to change the proving system as well. So Groth 16, Jens Groth came up with this really small and efficient, probably the most efficient pairing-based ZK snark that at least that I know about, and that academia knows about. So we're switching to this, and the proofs are smaller, and it's a lot cheaper to construct the proofs and so on. And the security model is generic group model. And then recently, I think late last year, there's a proof in the algebraic group model, which is nice, clean, much more clean and much more conservative than the generic group model. And also parameter generation. So obviously with ZK snarks, we have to construct the ZK snark public parameters for everyone to create and verify proofs. And the way that we did this for the first ceremony is that we had 6 people, and they performed a multi-party computation, and only one of them needed to be honest for the resulting parameters to be safe. If they weren't safe, then they'd be in the sense that someone could create counterfeit Zcash. After sometime earlier last year, I was exploring along with Ariel Gabazon and Ian Myers different ways that we could improve the scalability of the parameter setup, and we came up with this protocol which could scale so that you could have basically an unbounded number of participants that participate with the same property that only one had to be honest. However, it split it into 2 pieces. There's one ceremony, which is called the Powers of Tau, and the Powers of Tau basically is agnostic to the ZK-SNARK circuit, so anyone can use the result of this ceremony for their ZK-SNARK project. And so that's been finished, and the Zcash Foundation was happy to collaborate and facilitate the coordination of that. And then there's a second phase, which is specific to the circuit, and we're performing this right now, actually. So if anyone's interested in participating in the Sapling MPC, so we're performing MPC for the Sapling's parameters, please email mpc@z.cash, and you can convince yourself, as long as your computer is not backdoored or something, that your participation in the ceremony was secure, and give you a little more confidence in the resulting parameters. So that's kind of the basic, foundation of the cryptographic updates, but there's a ton of new stuff on top of that. So we improved the performance of the underlying ZK-SNARKs and the proving system and so on, but what we're doing in the Sapling upgrade is we're keeping the existing Sprout Z addresses. We're leaving them the way they are. They're a little bit faster now. We're adding a new type of Z address, which is much more efficient to send and receive payments with. So kind of just to give a little recap of how this stuff works, how Zerocash works. This is this is different terminology than what they use in the Zerocash paper, but this is kind of how we describe it. In Zerocash, you basically have notes, which you can think of as kind of like unspent transaction outputs in Bitcoin. They basically have a value and some predicate, an address that's allowed to spend it. And we place commitments to these notes, these cryptographic commitments, inside of an accumulator. In the case of Zerocash, in the case of Zcash, we use a Merkle tree. Because we have ZK-SNARKs, we can use a gigantic Merkle tree to protect people's anonymity and privacy. And so once your note's in the tree, in order to spend it, you prove that it's in the tree, and then you simultaneously have to reveal this thing called a nullifier, or a serial number, which kind of uniquely fingerprints the thing that's being spent, but it doesn't identify what's actually being spent, which node it is that's being spent. So this is kind of the fundamental concept. This basic framework is kind of how CryptoNote works and other things as well. But obviously with Zerocash, we can use these big Merkle trees with snarks, and that's kind of the benefit of ZK-SNARKs. So in order to make the rest of the construction really efficient, and all these components, like every single one of these things, these notes, the accumulator and the nullifiers, we have to choose cryptographic primitives that are really efficient to evaluate inside of ZK-SNARKs. So the main breakthrough involved in Sapling is this combination of elliptic curve-based primitives that and a bunch of circuit optimizations and things like that that are really interesting. There's this thing called JubJub, which is an embedded elliptic curve. It's a curve that's really efficient to reason about inside of the ZK-SNARK construction. So on top of this embedded curve, we construct these things like Peterson hashes, which is a collision-resistant hash function that we can construct a Merkle tree out of and significantly improve performance from that. We can also build other kinds of elliptic curve primitives inside the circuit, like Peterson commitments and other kinds of like value commitments, which kind of can be used to ensure that value is balanced between inputs and outputs and things like that in the construction. And we can also use different kind of structures in our keys that are more asymmetric, so to improve performance. The addresses in Sapling they're shorter, which it's not really a goal at this point, but they only contain one group element, which is a point on the JubJub curve, and they have this really nice key design that, because we've been able to do much more sophisticated stuff, we were able to make these viewing keys, which you can see the incoming and the outgoing. In the Sprout construction, you couldn't see the outgoing payments. And also, the addresses have this cool feature which allows exchanges and merchants that are interested to receive on trillions of addresses simultaneously without any overhead, which is really useful for promoting these shielded transactions, because every single time there's a payment on the Zcash network, everyone has to try to decrypt the payment to see if it was to them. And so if they have to do it for 1 billion addresses, it's not really ideal. You can kind of speed it up a little bit, but we needed to modify the construction so that these addresses could be distinct and unlinkable, yet you could receive on all of them at once. So it's very useful. The other major difference from the original Sprout construction is that we split the circuit that we use in the construction into 2 pieces. One is the inputs. They have their own proofs and so on, each one of them individually. And then the outputs have a different proof as well. And so 2 different circuits. This is a diagram here of the spend circuit. So what is kind of all the construction and everything, every little piece that's talking to each other inside the ZK Snark circuit for the spend circuit. And so, yeah. The performance improvements in total, I guess, we get close to about 2 times performance just from the ZK Snark and elliptic curve improvements alone. And on top of that, we get an additional about 8 times improvement, but probably closer to like 20 or 30 times, depending on what you're doing, improvement in performance in general. So that takes, what would take maybe 40 seconds on my computer at home, about 2.5 or 3 seconds instead, which is amazing. It actually makes it possible for us to put shielded transactions on mobile phones, which is, and perhaps other things like that. So yeah, very crucial. Another kind of interesting thing that I actually forgot to put in the slides is that the construction is designed so that hardware wallets can perform signatures on shielded transactions without needing to perform the snarks themselves. So we've kind of split the logic of spend authorization away from the snark. So in theory, I don't know if it will happen, but Trezor or some other hardware wallets can perform these side channel resistant whatever signatures inside the wallet, but outside the wallet you can have the host computer that's already being trusted with privacy perform the ZK Snark proof or create the proof. And so we've designed the construction to kind of allow for hardware wallets as well. So it's exciting. So another kind of fun thing about Sapling is that most of the cryptography is actually written in Rust. So the elliptic curve, the proving system, all of the circuit-related stuff, all the bridges and FFIs and everything that connects to our actual C++ code base, and also the multi-party computations. The powers of tau I've implemented in Rust, and actually some others have implemented in another language as well, using a different toolkit. This phase 2 library that you see is actually, you can use this yourself if you want to perform your own MPCs using the powers of tau to perform your own MPCs for your own ZK Snark circuits. That is a cool little library that lets you do that pretty easily as some documentation. Love to see some people try to use that. And Sapling MPC, the MPC that's currently ongoing, is actually built on top of phase 2. So, yep, that's it. I was supposed to announce Ariel is coming on the stage.